And we're back. Welcome back from the weekend and happy Tuesday. Today, we will talk about VC dimension and finish up our discussion on learning feasibility. Before we begin, some administrative bits. The reading for this material is in the text, section 2.1.3 through 2.2.4, which is pages 50 through 62. Homework number 1 will be on the blackboard, and it is due a week from today, Tuesday, the 16th of February, on the 23rd of February, a week from today, at the usual 11:59 and 59 seconds. So when we last left off, we talked about the bound on B and K, the maximum number of dichotomies on a data set of size n given a breakpoint of K. And we showed that it's bounded from above by this expression, which we then demonstrated as polynomial with a degree of K minus 1. And we showed that if you have a polynomial expression for this bound, learning is feasible because the negative exponential subsumes the dampening of this bound. We also went back and we showed that this works, this bound, with the positive rays, the positive intervals, and the 2D perceptron. So let's take a look at the VC bound. Now, when we talked about Hoeffding's inequality, we spoke about a guarantee that in-sample error tracked with out-of-sample error. And we introduced a probability P of x that gave rise to the vector instantiations that you received for your data set. Now, let's take a look at a large space in this Venn diagram, the space of all possible data sets. Now, for a given data set, that's just one of them. But when we look at this bad event, remember that Hoeffding's inequality has this Eout term. And when we talk about Eout, we're talking about an expectation, a probability over data sets. And so this idea of the bad event concerns data sets for which in-sample error diverges from out-of-sample error. So if we identify all of those data sets that share this quality, that's this red squiggle, all of those data sets collectively for which that bad event happens. Now, of course, the proportion of those data sets relative to all the other possible values that a data set can have is very, very small. And Hoeffding's inequality, the right-hand side, will be bounded from above by a relatively small probability. And what that means is that it's very rare that you're going to visit this particular or those parts of the space of data sets where En and Eout diverge from one another. And so we had extended that to a set of hypotheses, and we took the single case for Hoeffding's inequality, and we did a worst case scenario and used the union bound. Now, with the union bound, we made the assumption that these bad events for each one of the hypotheses visited from our hypothesis set, that they do not overlap. Now, of course, if you have an infinitely sized hypothesis set, by the union bound, you're going to fill up this hypothesis space with the union of all of the bad events, or you're going to fill up the space of possible data sets with the union of all of these bad events. And that means is that if M is infinite, the size of the hypothesis set is going to be very likely that En with a high probability is going to diverge from Eout. Okay. Now, we're going to make it easier by assuming some overlap. And this is what the growth function did, but it did it for in-sample error. And we looked at how En, how far it was from out-of-sample error, and this growth function essentially took an infinite number of hypotheses and collapsed it into an equivalence class defined by the dichotomies. The number of hypotheses is now defined by the dichotomy that they give rise to. And so the growth function pertains to in-sample error. It deals with the samples. But if you look at Hoeffding's inequality, we have E in, but we also have E out. And this E out makes our life a lot more difficult. Why? Because it deals with out-of-sample error, and we have that probability governing the occurrence of the vector-valued instantiations, i.e. the different data sets. It's going to refer to the entire space of data sets. So because of that, we can no longer collapse to dichotomies. We need some way of getting rid of out-of-sample error because we want to avoid this idea of dealing with that space of possible probabilities, giving us data sets and needing to take expectation for that on the hypothesis. We have to deal with the full hypothesis. So this would again fill up the entire space of data sets using the union bound for E out. It's just not going to work. So the solution to this is called the VC bound. And what the VC bound does in a clever way, it assumes that there's overlap between bad events. So let's take a look at what this VC bound does. And so in the single bin scenario, we have a sample, En, from the bin, and all of those marbles that are still in the bin. Well, the error with respect to the hypothesis from our hypothesis set is E out. But you don't necessarily have access to that probability distribution giving you these marbles. Now, of course, one of the things, and that was done, which is a very elegant proof, was instead of taking one sample, take two samples. So the sample size increases then from N to 2N. The first sample is going to be N many samples in sample from our bin, and we're going to call that En of H. And then the second sample, we're going to sample one more time. We're going to call that En prime of H. And so when you have a single hypothesis, that means you're learning, means that you're trying to determine if learning is feasible, governed by Hoeffding's inequality. And it's possible then, if you're going to pick two samples, that En of H is going to diverge from E out of H. And so En, as a single hypothesis, tracks with E out as governed by Hoeffding's inequality. Likewise, En prime of H, and that should be En prime of H, is also going to track with E out. And so if En of H tracks with E out and En prime of H tracks with E out, that means they also will track with each other because they're both tracking with that same E out as defined by Hoeffding's inequality individually. So if they do that, track with one another, okay, well, seeing if they diverge is the same as seeing if they diverge from one another. En diverging from En prime of H. And so by focusing on two different samples, we can use the coincidence or the tracking between En of H and En prime of H. And in doing this, we avoid this situation where we have infinitely many hypotheses to look at because we're focusing on E out from before. Because when you focus on E out from before, well, E out looks at this distribution, okay, and then for each distribution, now you have to consider all of the hypotheses. You can no longer collapse them down as dichotomies because now you're looking at all of the possible data set instantiations. So what this construction does is it avoids considering infinitely many hypotheses that would have happened when, if we had had to focus on out-of-sample error. And so you do have a bigger sample. You have 2n many data points, but because you're focusing on the coincidence or the tracking between En of H and En prime of H, now you can focus entirely on dichotomies and not on the infinite number of hypotheses. And so that's what the VC bound does. So from before, we had the probability that E in diverges from E out, exceeds your error tolerance epsilon, is bounded from above by 2 times the growth function in n, e times e to the minus 2 epsilon n. And with this construction, it's similar but not quite the same. We see a doubling here from 2 to 4. Well, that's because it's 2 different samples. The growth function, instead of n, we have 2n. But then we dramatically reduce the effect of this exponential from minus 2 to minus 1/8 epsilon squared n. And so a single hypothesis means learning is feasible, and we can pick samples such that E in of h and E in prime of h will diverge from one another. And this expression down below has a name, and the proof is in the appendix of the text. This expression is called the Vapnik-Chernovenkis inequality, or the VC inequality, or the VC bound. So that's our VC bound. It's a clever way of removing or eliminating the impact of E out so that we can now collapse the effect by looking at when E in and E in prime diverge from one another. All right, so let's take a look at the definition more formally of the VC dimension. And so the VC dimension of some hypothesis set, H, or DVC of H, is the largest data set size n for which the growth function on that data set is equal exactly to 2 to the n. So it's the largest number of points that hypothesis set H can shatter. And so this n, the data set size, as long as it is at most DVC, the VC dimension of your hypothesis set, that means H can shatter all n points. But by definition that we had for the breakpoint, we can no longer shatter, so K then is greater than the VC dimension of hypothesis set H, DVC of H. So relative to the breakpoint from before, we said the growth function is bounded from above by this expression, the sum for I goes from 0 to k minus 1 of n choose I. And we said that this is at most, this upper bound, this quantity on the right-hand side of this inequality, that quantity, it is polynomial with a degree of k minus 1. So relative to VC dimension, we can also bound our growth function to be at most the sum I goes from 0 to the VC dimension, DVC, for that hypothesis set. And so this gives us, in similar fashion, the highest degree polynomial for this bound on our growth function is going to be polynomial in the VC dimension. So we have our examples from before, and we'll bring these back out. And we said the positive rays. Remember the positive rays? We said that once the data set grew to size 2, that was our breakpoint. And so for the positive rays, the VC dimension is 1. For the 2D perceptrons lying on the plane, once we went from 3 points to 4, we could no longer shatter the data set of that size. So the VC dimension for the 2D perceptrons, DVC, is equal to 3. And then for convex sets, DVC is infinite. So as long as we have a finite VC dimension, this bound will be polynomial. All right. So let's take a look at implication of VC dimension on learning. So the VC dimension does not depend on a choice of learning algorithm. It focuses entirely on the hypothesis set, and so it does not care or depict how you approach the search for selecting what your final best hypothesis G is. It also, this VC dimension, doesn't depend on the input distribution. The specific samples are selected so that you maximize the number of dichotomies. You pick the points. It also does not depend on the target function. It doesn't depend on Eout, out of sample error. The bound depends on in-sample error, and you're using the coincidence between the two errors, E in of H and E in prime of H. So we're completely taking out this issue associated with looking at an infinite number of hypotheses. And it does depend on the hypothesis set the training examples, because we're sampling 2n, and the final hypothesis, which is what the divergence that we're evaluating is on. So let's take a look at an example for the VC dimension of the perceptron. Now we said for a two-dimensional perceptron, now remember, let's distinguish between the dimensionality of the perceptron and the dimensionality of the model. The model is a combination of the hypothesis set and the learning algorithm. In order to build the model for the perceptron, remember we augment the weight vector with a W naught and augment the feature vector with an X naught. And so for a two-dimensional perceptron, the model would be 3 dimensions. The VC dimension is equal to 3. More generally for the perceptron, the VC dimension, DVC, is going to be D plus 1, where D is the dimension of that particular function class. So if we had a line on the plane, that's a two-dimensional hypothesis set. When we build the model, we augment it with W naught. So we're going to prove this DVC is equal to D plus 1 by showing two cases that the VC dimension for the 2D perceptron is at most D plus 1, and the VC dimension for the perceptron, the 2D perceptron, is at least D plus 1. So let's focus on this first one, at least D plus 1. So let's choose the data set size n to be D plus 1 many data points. And each one of these data points is in D-dimensional real valued space. And so our data is in R super D. Now, of course, if we have D plus 1 points in R super D, it's a fact from linear algebra that the D plus 1th point can be computed through a linear combination of the other points. Okay? So now let's populate our design matrix, and this design matrix is a row matrix, and in each row is one of our D plus 1 many vectors. So we have X1 transpose, X2 transpose, up to and including XD plus 1 transpose. And it's important to note that in this design matrix, each one of our row vectors, Xi transpose, is going to be in the form of X naught followed by Xi1 through Xid. And so this is the augmented feature vector in R super D. And so given this definition, of course, if we were to look at the rank of this matrix, we find it's a square matrix because we're going to have D plus 1 many columns, and we'll also have D plus 1 data points, so it's going to be D plus 1 many rows. So this design matrix is going to be D plus 1 by D plus 1, so it's a square matrix, and square matrices are invertible, have non-zero determinants. So let's choose this particular data set because you pick the points. Remember, we augment with X naught set to all ones. So we have that from before. And we're going to set the first one to all zeros, but we're only going to set the diagonal elements to all ones. Now, this is definitely invertible. The determinant is 1, which is certainly non-zero. So X, our design matrix, is square, and square matrices are invertible. It's just 1 over the determinant times the matrix of cofactors. So let's now take our target vector y, and y has an entry for each one of those corresponding D plus 1 many vectors. So here we have y1, we have y2, up through and including yd plus 1. And so with this y vector, you can choose any instantiation of plus 1 or minus 1, and thus any dichotomy. And now the goal is to find that vector w augmented, including the w naught, for the final best hypothesis, such that it can generate all possible dichotomies. And so we have sine xw is equal to y. In order for sine xw to equal to y, one of the things we can do is just choose the value of xw exactly equal to y. Now, of course, because it's a square matrix, x is invertible. So if we left multiply by x inverse, well, Here's left multiplied by x inverse, left multiplied by x inverse. This goes to identity, and we're left with w is equal to x inverse times y. Now, of course, this is for precisely d plus 1 many row vectors representing the data points. Recall we have x1 transpose up through xd plus 1 transpose. Now, we said there are d plus 1 columns and d plus 1 rows. Now, of course, if we added another row, x transpose d plus 2, well, that's now a d plus 2 by d plus 1 matrix, our design matrix X. And that's no longer square. It's a rectangular matrix. And a rectangular matrix is not always invertible. It can sometimes be non-square and still be left invertible or right invertible. Now, left invertible means that you left multiply by inverse and it produces identity, but not through right multiplication by an inverse. And so we can absolutely, we showed, have d plus 1 data points and produce all dichotomies, but we can, in some cases, have more than d plus 1 data points, i.e. d plus 1 rows, or d plus 2 total rows. So that being the case, with this, we've shown that we can have at least d plus 1 as the VC dimension for a d-dimensional perceptron. Now, of course, if d is 2, that's a line on the plane. If d is 3, it's a hyperplane in three-dimensional real-valued space. If d is 4, it's another hyperplane. And so that means DVC for the 2D perceptron is at least d plus 1, and we've demonstrated that mathematically with our construction. All right, so with that, I'm going to end there. And again, homework is on the blackboard. As usual, please stay healthy, stay safe, and I will see you all on Thursday.